Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at semi-primes and Euler's totient function. Let's start with semi-primes. So they're very important in number theory and in particular cryptography that we'll see. So a number is semi-prime if you can write it as the product of two not necessarily distinct primes. So something like 35, you can do that. Just look for its prime factors. Its prime factors are 7 and 5. I can write 35 as the product of these two numbers, which are both prime. So that means 35 is a semi-prime number. It is not a prime number, but a semi-prime number. Its factors are 1, 5, 7 and 35. It has 4 factors. On the other hand, 42 is not semi-prime. If we look at its prime factors, it's 7 times 3 times 2. So there is no way that you can write this as just two prime numbers multiplied together. You can write it as 3 prime numbers multiplied together, but not 2. 42 has more than 4 factors. 1, 2, 3, 6, 7, 14, and so on. It's got more than 4 factors. It's not a semi-prime number. 49 is a semi-prime number. It's 7 times 7. I can write it as 2 prime numbers multiplied together. It doesn't matter if those prime numbers are the same, if they're not distinct. So 49 has just 3 factors, 1, 7, and 49, so it's semi-prime. 56 is not a semi-prime number. I can write it as 7 times 2 cubed, so I can write it as 4 prime numbers multiplied together, but I can't write it as just 2 prime numbers multiplied together. So 56 has more than 4 factors. 1, 2, 4, 7, 8, 14, 28, etc. So this one here is not semi-prime. All right, let's now look at co-prime numbers. So two numbers are co-prime if their highest common factor is 1, which means they have no prime factors in common. So 55 and 85 are not co-prime. The highest common factor of these two numbers turns out to be 5. So they share a prime factor of 5. They can't be co-prime. On the other hand, 32 and 99 are co-prime. Their highest common factor is 1. So how do I know that their highest common factor is 1? Well, the only prime factor of 32 is 2. 32 is 2 to the power of 5. 99 is 9. 3 squared times 11. They don't share any prime factors. So co-prime numbers are very important in number theory and cryptography. We're now going to look at something that counts co-prime integers. So as the name suggests, Euler's totient function is a function. That means it has an input and an output. So you input into this function phi of n, a positive integer n, and the output is the number of integers less than or equal to n that are co-prime to n. So what does that mean? Well, let's look at phi of 8. So this will be equal to the number of integers less than or equal to 8 that are co-prime to 8. So let's go through and count them. So 8 has its only prime factor 2. So anything that is divisible by 2 will not be co-prime to 8. And the numbers left over, 1, 3, 5, and 7, they are co-prime to 8. So phi of 8 is equal to 4 because there are 4 numbers less than 8 that are co-prime to 8. What about phi of 20? Well, 20 is 2 squared times 5. So its prime factors are 2 and 5. So we'll go and cross out all of these numbers that have a prime factor of 2, and then we'll cross out the ones left that have a prime factor of 5. So you can see that there are 1, 2, 3, 4, 5, 6, 7, 8 numbers left. Phi of 20 is equal to 8 because there are 8 numbers less than 20 that are co-prime to 20. But let's look at some properties of this function to help us out. You can imagine that it would get very tedious to calculate phi of some large number. So here are some rules that can help us with the counting. So in this topic, whenever you see p, we're talking about a prime number. So if you take phi of a prime number, it's equal to p minus 1. For example, 43 is prime, so phi of 43 is 43 minus 1, which is 42. Now this makes sense. Because 43 is prime, its only factors are 1 and 43. That means it doesn't share any prime factors with 42 or 41 or 40 or 39. It doesn't share any prime factors with any number less than 43. So that's why it's 42. So this rule here says that if A and B are co-prime, phi of their product is just the product of their phis. What does that mean? Well, for phi of 70, 70 has its prime factors 7, 5, and 2. So we can write phi of 70 like this. Now I know this rule had only 2 numbers here that were being multiplied, but it really works if you're multiplying any number of positive integers together. Now, writing it like this makes life easier because these are prime. We can use this rule again. So phi of 7 is 6 because 7's prime. Phi of 5 is 4, 5 minus 1. Phi of 2 is 2 minus 1. So phi of 70 is 24. That's so much easier than going through each integer from 1 to 70 and deciding whether or not it's co-prime with 70. So this rule here is about prime powers. Once again, if you see p, it means prime. So let's look at something like phi of 128. So 128 is 2 to the power of 7. So rather than going through each integer from 1 to 128 and seeing if it's co-prime, we'll use this rule. Here, p is 2, k is equal to 7. So this rule tells us that phi of 128, it will be 2 to the k minus 1 will be 6 multiplied by p minus 1. So 2 to the power of 6, which is 64. That makes sense because the only prime factor of 128 is 2. So all of the odd integers are co-prime to 128. All of the integers are not co-prime. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.